Hello. Once again, this is our third lesson in our course of calculus. Now, the lesson that we gave before concerns numbers. And of course, we had to give numbers first, because if we speak now about functions, and this is our lesson, functions, they operate on numbers. So we have to give number first, and then we switch over to functions. Now, functions, it's known very well that a function is a kind of relation. And but the term itself, the one who give this expression of a function is Leibniz. And it is known that from last lesson that we have two sets, and a function is a relation which maps a certain x in the first set into another y in the second set. So for each x in A, in the first set, which is A, there corresponds, as a matter of fact, a unique value in B. If this is so, and we can scan all the x's in the first set, then we are speaking about functions. But in fact, this definition of a function is a little bit vague, because when Leibniz was speaking about function, he spoke mainly about variable associated with graphs. In other words, he has a curve of equation y is equal to f of x, and he speaks of x and he speaks of y. But then you need a more aggregated idea of a function. And it was actually Euler in the late 18th century, a Swiss mathematician, a very renowned one of the four most renowned mathematicians in the history of mankind. He himself gave a better understanding, or a better definition of a function. What he said is that you have a function is a relation or a correspondence rule between two elements in two different sets, where one can calculate y, or assigned a value for y based, called the dependent variable, based on another one in the first set, which is the independent variable, let it be x, for example, which can be chosen freely. And actually this definition of function was more general, so that not only it applies to real functions or real variables, but it applies also to complex functions. Now, usually in economics, since this is the subject that you're studying, all the variables are real. But in engineering or in physics, etc., we may encounter some other sort of variables. Like, for example, you have square roots of values that are negative, and therefore you are speaking about a different sort of function. But here, since all the variables, they are salaries, they are growth, inflation rates, power functions of like production function, cost, etc. So we are dealing mainly with real variables. Now, in our lesson of today, we shall be speaking about the concept, what's the meaning of a function. Then we move to the function as a machine. Then we speak about some kind of functions like discrete, continuous, and the function as a set of ordered pairs. And then we speak about combinations of functions. Now, what is the meaning of a function? Now, a function is, if we go back in history, usually mathematicians, they associate functions with an equation of this sort. Y, for example, is equal to x cubed minus 3x plus 1, and they call this a function. As a matter of fact, it's not a great mistake. I mean, you as a student, you can utilize the same approach or the same sense of a function, like you say y is equal to f of x, and f of x is a function. There is no great harm done if you do so. But then the mathematicians, they encountered special cases in which their definition of just y is equal to f of x failed. Like, for example, the first instance here, you have on the left-hand side above, you have a function y is equal to 1 over x, and its peculiar operation done on this function is that you cannot substitute x for 0. What you do, the meaning even of a function, what's the meaning of a function? The word function itself, that it means that you are functioning or you are operating on something. You are feeding something and you're getting something out of it. You perform a certain function. And the best approach of this is to use your calculator. Now, your calculator has a button entitled, or on it is written 1 over x. In other words, you can feed in any x and get 1 over x, except that when you feed x equals 0, you get a letter E, meaning you have an error. In other words, this function here, it operates as a machine, except that when x equals 0, it doesn't function. So there is a problem here. Now the second one here also, you have y is equal to square root of 1 plus x. Here again, if you put x is equal to minus 3, for example, you have a square root of minus 2. Actually, there is no harm done if your value is square root of minus 2, except that here we speak of something called the codomain. I mean, the thing which we are allowing as functions. We only are entitled in our course and in practical applications, I mean practical real-life problems, that we deal only with real functions over real variables. So x is real, but again, the value that is given for f of x, or the value that you determine or you calculate for f of x, is also real. So here we cannot take x equal to minus 3. In other words, unless x is greater than or equal to minus 1, you fail to calculate square root of 1 minus x. So again, here there is another problem. A third one is y is equal to square root of x. Here there is no one rule for this function. You may have for x positive is equal to x, and for x negative is equal to minus x. So you have a double phenomena for the same function, once for positive x and one for negative x. And this is why when you say just y is equal to f of x is a function, is no more good, because you have to differentiate between f and f of x. F is the function itself, and f of x is the operation that you perform, and you seek to determine f of x provided that f of x exists and it has to be real. Now, and for this, mathematicians try to give a little bit of a more approach to functions. So what they did is that they say a function is a law of correspondence, or a correspondence rule that maps some x in a set or a partial set of a larger set A into another set which lies into a bigger set B. A and B can be taken as the set of real numbers, or segments, parts of real numbers. There is no strict rules for this. And D of f here, we call it the domain of the function. So the domain of the function comprises all possible x that you can use. For example, for 1 over x, for example, what are the possible x you can use? There is no such x which you cannot feed into the machine and does abstain from giving you f of x. It's always giving you f of x, except the value x equals 0. So here the domain of the function comprises or contains all the possible x's which are amenable or the ones that you can really work with. This is called the domain. And then the value of x here, when you feed it into f, it transforms, it maps into an image set. The other part, or the other side, which is the value of y, and value of y is contained in a bigger set called B, and this set called B is called the codomain of the function. So the codomain is, in fact, of the function is a part of the ingredient of a function, because it tells you what kind of function it is. Suppose, for example, you are dealing with square root of 1 plus x. So suppose you restrict your f of x to be real, then you cannot accept x is equal to minus 3 in square root of 1 plus x. But if you can accept, and you say that B, we remember we spoke about the real number, and you said that R is contained in a larger non-order set called Z, which is the set of complex numbers. If you accept complex numbers as values for the values of your function, then you may very well accept to feed into your machine, into your function f, the value of x equal to minus 3. But since you restrict your function to be real, then your codomain tells you that you are only dealing with real numbers, and therefore this value of y has to be real, and the totality of all the values of y is called the range of f. So now you have the function f, which is responsible for the transformation from x into y. You have the domain of f, which comprises all the possible values of x which you are entitled to use, and you have the range of f, which are the values of y, all possible values of y, when you feed all possible values of x, and this all possible values of y are contained in a larger set called the codomain of the function. So f, in fact, does some mapping from the domain to the codomain of the function. So now we have the characteristics of f. What are the ingredients? What are the elements of f? First of all, there is the rule f of x. When you say, for example, y is equal to x squared, this is the rule. This is called the rule, the one that you feed in x to get f of x. And then you have the domain of f. And the domain of f contains all the possible values of x which you can use. So, of course, this you have to know. And then also there is the codomain of f. Usually for students, since we are dealing with real numbers really, there is no reason why we should say that the codomain is R and we restrict ourselves to that the range of f be restricted as a subset of a big codomain R. Why don't we just say that the function maps from the domain into the range just for simplicity? Of course, this is not exactly so. It has to be a larger concept to utilize. But if we say this, it doesn't matter, so long that we restrict the codomain to the range. Since we are using the range, or we are calculating the range only, therefore we can say simply that the function is given by two things, the rule and the domain of the function. And we take the codomain to be R or restricted to the range. Of course, the range is not part of the elements of f. Why? Because we can calculate it. Knowing the rule and the domain, we can get the region of the range of the function. And this is why there is no point of putting it here and listing it along with the three main elements of the function. So this definition of function we give is it's so large, it's so broad, it's so general, because it can apply to anything really. It can apply to people, correspondence between people, between books, between planes, between lines. So why don't we restrict ourselves to the function that we shall handle, the function that are listed in our lessons only of Calculus 1. So we shall speak of real functions only. So a real function f is a rule of correspondence which assigns to every element x in a subset D of R. We shall take the domain D part of a greater region or set R, and it maps D into a unique element. And this we said in our last lesson, it has to be a unique element in the image set of B in the codomain. So you have a unique element in R, since we are dealing with real variable only. So we can say that our real function, it maps D into R from the domain till the real set of numbers, the set of real numbers. So D stands for the domain, and this totality of all f of x in the codomain, which is inside the codomain, we call it the range of f, and of course it would be a subset of R. So now we go back to the functions that were posing some problems. Now the first one, y is equal to 1 over x. Now there is no problem, because since y has to exist and has to be real, then we cannot put x equal to 0. So here again, the domain of the function is what we call the proper domain. In other words, all the possible values that we use are the ones that we use on your calculator. The calculator will never refuse to be fed with any number, except when you put x equals 0, then there will be a problem, and it gives you a sign of error. So therefore we say that the domain of this function is R except the number 0. Again, y is equal to square root of x. This is the rule of the function. And this function here, again, does not work for all of R, because we said before that we are only accepting real values for y. So we cannot feed in x here equal to, for example, -6. We can only start from -1, because this gives you 0. And any value of x greater than -1, it will be positive, so we'll accept this value. So we say in this case that the domain of this function starts from the value of -1. In other words, the domain of f is equal, it ranges from in the closed interval from -1 till infinity. Of course, here we took the proper domain of the function. In other words, we spoke, or we listed all the possibility of x. But you might as well say, for example, that your rule of the function is square root of 1 plus x, but I shall restrict myself only to the values of x between 0 and 1. I'm free to take the domain of my function from 0 to 1. In other words, I shall only accept these values. I'm free to do so. But in general, if you are speaking about the totality of values of x, then in which case you can take all the values ranging from -1 till infinity. Here is a function y is equal x square. This is a function which is, it's called actually, when we spoke about the codomain R, the range could be a subset of the codomain. For example, here, this function has domain R because x square, when you're on your calculator, when you use x square, any value of x, it will work out. There is no such value which the calculator will abstain to function. So the domain is R. But the range, you will see that the range here, x square, is always positive. And therefore, your range here will be starting from 0 till infinity. So if we take the codomain as from 0 to infinity, we say that this function is onto function, is the other word, or surjective in English, meaning that the range of the function takes all, constitutes or is broadened such that it takes all the set of the codomain. In other words, it's not a part of it, it's not a subset, but it's all of it. However, if the function, only the range of the function only constitutes only a part of the codomain, then we call this function into. So actually this function into, if you take the codomain as R, as we had before, then this function, the range of the function which stands from the closed interval from 0 to infinity, only stands as a subpart, only a part in the greater codomain, which is the set of real numbers. Now when you say y is equal to s squared, there is one important thing here. Mathematician, of course, as a student, I told you before that you can say y is equal f of x is a function. But mathematicians usually, they differentiate. And the best thing to understand this is your calculator. When your calculator function, there is a button called x square on it, meaning that you are squaring what you are feeding in. So if you are feeding x, you get x squared. But if you are feeding y, you get y squared. If you are feeding beta, you get beta squared. So the important thing is not what you are feeding, but the operation itself. So y is equal to x squared, you're speaking about a quadratic function. It's a squaring function. And same thing here. Here doesn't mean that y is equal to x squared. It means that x is equal to plus or minus y. No, we don't mean this here. We are not solving this to get x as a subject. On the contrary, we're just speaking about the operation itself. What you are doing here, what function you are doing, you are squaring. And here as well, you are squaring. And therefore, whether you are saying y is equal to x squared or x is equal to y squared, again, this is the same function. And this is why mathematicians, they like to consider the function as a machine. How? They have a box like this in which they feed x, and from the other side, you get f of x. In other words, this machine is fed in with x, and it delivers f of x. And f is the machine itself. Of course, here now you differentiate directly between f and f of x. F is the machine itself, the operation, whereas f of x is the output of the machine. It's like, for example, you say a mincer and a minced meat. Of course, there is a difference between a mincer and a minced meat, or a juice extractor and juice itself. There is a difference between the two. And this is why in most books, what they say, for example, when they give you an example, they tell you, or a problem, they tell you, for example, if the function f is such that f of x is equal to x squared, why do they differentiate between the two, f and f of x? F is something, and f of x is the output from the machine. But as a student, as I told you, there is no big harm done, because it's understood what you are doing is the operation itself. So functions also can be discrete or be continuous. For example, this is a discrete function. It maps discrete value of x into discrete values of y. You have here the two sets A and B. For example, let us take an example. Suppose, for example, the set A comprises all possible. You are in a school, and you have all possible students in the school. The set of all students in the school, and B here the set of all fathers of these students. So you can pick up a few students, for example, and you say, for example, f. There is a correspondence between each student in this set of students into some other set y of fathers, which is contained in a larger set of fathers. Of course, here x, as you see here, for each student there is a father. And you may also accept that two students or twin, for example, in the same school have one father. This is accepted. But what you don't accept is that you have one student corresponding to two fathers. You can't have a student having two fathers, but you can have two students having the same father. And you see, this exactly comply with the rule of a function. Here we have the function f, the operation itself, and the mapping itself from x into y, and you have the two sets, the domain of the function, and you have the codomain of the function. So we call this a discrete function. But again, you can have the numbers of row of arrows, which goes from the set A into the set B to be infinite, like this one, for example, here. Here, x can take all values ranging from -infinity till 1. How did we calculate this? It's easy. All you have to do is that you take what's inside the square root to be positive. So 1 minus x greater or equal to 0 implies that x less than equal to 1. So the domain is all values of x less than equal to 1. But you may well, and this is the domain or the proper domain of the function, but you may well take, for example, as I said before, the domain to be restricted to the interval from -1 to 0. You are free to do that. This is a representation, for example, of how functions work. Now, we spoke before of functions as a Cartesian product of ordered pairs, mapping elements x in domain, a set A into another set B. Here, this is one of the ordered pairs, A and B. And actually, these set of ordered pairs can constitute a graph y is equal to f of x. But this same D domain can stand for can be elements of other functions. For example, when you say x squared or x cubed work on R. Any value is squared, and x cubed as well. Any value you take the cubic the cube of it. So when you say x squared, you work on all real numbers, and also when you say x cubed, you work on all real numbers. So both of them, as a matter of fact, have the same domain. And here as well, you have, for example, y is equal to f of x, but this doesn't mean that f here has the only domain d of f. You may have other functions that have the same domain. But here, you chose only those pertaining, you remember in the last lesson when you spoke about the relation Q, you chose only those pertaining to a certain relation, and this relation is adjusted by the rule of the function. So here you are speaking about a specific function, but you may very well take another function working on the same domain and the same range. Like, for example, let's say, for example, you have a sphere. If you cut the sphere by a plane, you get a circle. So the area of the circle maps every r into pi r square, which is the area of the circle. But also, if you want to the surface area of the sphere, it maps r into 4 pi r square, or the volume of the sphere, it maps r into 4 over 3 pi r cube. So all the three functions have the same domain from 0 to infinity, and the same range also from 0 to infinity. So whereas each function can have a different unit and a different characteristics, all of them can be functions working on the same domain and the same range. And of course, they are part of a bigger Cartesian product of a larger set A and B, which can be R and R. In other words, you have a great Cartesian product, and in this Cartesian product, you choose a specific one of them, but you may always find others which have the same domain and the same range. This is a trivial problem. Determine the domain and range of y is equal to square root of x. Now, y is equal to square root of x. This we saw it before. It's called the absolute value of a number, and it's on your machine. Now, the absolute value of a number here, what's in the domain of f? The domain of f is r, because any value, in fact, this function works on complex numbers also. But regarding our lesson, since you are only dealing with real values, so we say that the domain of this function is r. Why? Because any value that you feed on the calculator and you calculate the absolute value, it gives you a value, and this is why we say that the domain is r. And whereas the range of this function is from 0 to infinity. Here it is. It's because it's always positive or 0. Determine the domain and range of f if you have some f like this. Now, this rule of the function is given as the form of three rules. In other words, there is no one such relation governing f of x. You can have just one, or like, for example, the one that you saw before, the modulus. It's true for x positive, it's x, and for x negative is minus x. So now you have two rules, provided it complies with the definition of a function. So there is no harm here. Here, all the values of x are perceived. There is no one such x that you feed in and you don't find a certain rule to work upon. For example, if you take x is equal to minus 1, then you are working with this rule here. Whereas for x equal to 3, greater to 3, it's equal to 1 from here. So here you have 2x plus 4 for x less than 0, which is this, and it's not defined at 0. Whereas x cubed here, it's defined between 0 and 2. In other words, for x equal to 0, it's equal to 0 and not equal to 4. It's less than 0, it goes to 4, but greater than 0, it tends to 0. And then from 2 onwards, it's equal to 1. Now, the domain of this function is always R, because there is no, as I said, there is no such x which you can't find a specific, any f of x or one of the f of x's in which you can feed them, you can feed in such x. But what about the range? The range lies from minus infinity till the value which is 8. Now there is no such, there is no value for y is equal to 8, because here x cubed is less than 2. So this 8, it's not at 2, it's less than 2, which tends to 8. So we say that the range is from minus infinity to 8. Again, this value of 8 is important. Why? Because this is, if we are, for example, you are interested to know what is the upper bound for this function, what is the maximum value which this function approaches to or attains. There is no such value. Why? Because it doesn't attain 8. It is less always than 8. So 8, we call 8 the least upper bound. It's an upper bound. Of course, we can take an upper bound 9. You can say that the range is always less than 9. But as the least upper bound is 8. In other words, there is no such lower bound which is an upper bound. The least of it is 8. So we call 8 is the least upper bound of the sets. Determine the domain and range of f if f of x is equal to x minus 1 divided by x plus 1. Here you have a function given by rule x minus 1 divided by x plus 1. This function here, directly, you see that you cannot use x is equal to minus 1, because if you take x is equal to minus 1, directly this value goes to infinity. So minus 1 is excluded from the domain of the function. So this is easy. Usually students find difficulty in calculating the range. The domain is easy because you can watch out from here. But the range of course, also it's easy. How? Well, you can look it out here. Suppose you put this equal to 1. Can x minus 1 equals x plus 1? It's impossible, because if you do so, then minus 1 is equal to 1. So 1 is excluded from the range of the function. In other words, there is no such y equal to 1, which calculated from this quotient here. But there is a better way of doing it. How? Is that you can solve x for y. Since y is equal to x minus 1 divided by x plus 1, so what is the value of x? Now x is equal to what? You can solve here. It's easy. You multiply yx plus y is equal to x minus 1, and then you set x equal to minus y plus 1 over y minus 1. Here you see directly that 1 is not in the domain of this inverse function. This is another function here which maps y into x, and I can't take y is equal to 1. So since I can't take y is equal to 1, I'm excluding 1 from the range of the function, and therefore the range of the function is equal to r except y is equal to 1. Now, the way you write functions, you can write it this way. You can say it's the set of ordered pair, but you may also write it in different forms. You can just say y is equal to f of x, such that x runs for all values of r except minus 1. You are free to do so. Here is another function. F maps x into square root of 2 minus square x. Now, what are the permissible values of x? Here directly you see that since we say that under the square root must be positive, therefore x must be always greater or equal to 0 because this is greater than 0. But again, square root is always positive, and we said before. So y, the value of y, is equal to the square root of 2 minus something. So it must be less than the square root of 2. It's easy. Again, we say that here x must be positive. So x is positive. The domain must be for all x that are positive. And again, 2 minus square root of x must also be positive. Why? Because it's under the greater square root. So 2 minus square root of x is positive, which means that x lies from 0 to 4. It's greater than 0 and it's less than 4. So the domain of the function lies in the closed interval from 0 to 4. What about the range? The range is easy again. Why? Because here the square root is always positive. So you always are above the x-axis. But till when? You see here that you subtract from 2 here something which is always positive. And therefore the range must be always less than square root of 2. So you can say that the range of the function here stands from 0 till the square root of 2. And the domain is from 0 to 4. And the range is from 0 to square root of 2. And you can write your function as follows: the totality of the order pair, and this is the rule of the function, and then you state the domain of this function, which is the proper domain of this particular f of x. Again, determine the domain of this function. So this function is complicated, but it shouldn't frighten you. Why? Because here we have modulus x plus 1, which is always positive. So all you have to do is to make sure what is inside the square root to be positive. How can we do this? We did this actually in lesson 2. All you have to do is to plot a line, and on the line, the region in which x minus 3 is positive, and as well as x minus 2 in other line, and 5 minus x here to be negative on the contrary. And then you watch out for the regions on the quotient to be positive. And you'll find this to be lying between minus infinity and minus 1. You exclude minus 1 because here minus 1 you cannot take minus 1. And then again from minus 1 to 3, and from 3 to 5, and after 5 you cannot take it out. Of course, here we cannot plot this direct from here. We have first to find the region in which this quotient inside the square root to be positive. And it's easy to be done. How? Like this. We watch out for x minus 2 to be positive. This is the region. For x minus 3 to be positive. And for x minus 5 to be, we inverted the bracket, what's inside the bracket to be positive. And we search for the region in which it is negative. So it's from minus infinity to 2. And then from 3 to 5. And we exclude 5 because we divided by 5. And so the domain is the closed interval from minus infinity to 2 with the union with the closed interval and open from 3 to 5, excluding x is equal to minus 1 because we divided by x plus modulus x plus 1. Of course, since we have a root, it's positive. So if you are seeking to obtain the range, it's easy. It's always positive, and it goes to infinity because you have roots in the denominator. But other values at which it is 0, yes. The values at x equal to 5 or at x equal to at 2, 3, I'm sorry, at x equal because it's in the numerator. And at the values near 5 and near minus 1, you have something called vertical asymptote, and the function is free to move till infinity. This is an easy function here. You don't have to manipulate with this function and draw something because 3x squared minus x plus 1, you know from theory of quadratic equations that this is always positive. And you can write it in this way. So if you write in this way and you complete the square, you directly notice the value. It's always positive, by the way. Why is always positive? The square root, does it equal to 0? Never. Why? Because what's under the square root is always greater than 0. It's the maximum value. You obtain it, of course, it goes to infinity. But the minimum on x is equal to 1 over 6. Because this becomes 0. So you only have 11 over 12. So the range must range from square root of 11 over 12 till infinity. In other words, you don't complicate life. you can complete the square and search for those values of x in which you can substitute here. What are the values of x which you can use? Any value of x you can use. Therefore, the domain is R. Whereas for the range, once you put it here like this, it's always positive what's inside the square root. And since it's always positive, it doesn't begin from 0. But it begins at the point at which x is equal to 1 over 6, because this is the least value for the function, and therefore it starts from the square root of 11 over 12. Now, we can also have combinations of functions. Like, for example, you can add up functions, and you can subtract functions, and you can multiply functions as well, and you can divide functions. It's like numbers. There is no problem with that. And when you do that, you have to watch for the domain. What is the domain of the combination? For example, you have f plus j, and you know the domain of f, the domain of j. Since here you request x to be fed into f plus j together, then the domain of this sum is equal to the intersection of both domains. So, for example, you may take f of x is equal to square root of 9 minus x squared, and g of x is equal to x squared minus 4. And you want to add them up. If you add them up, you get this. And the domain is what? The intersection between both domains. Now, the domain of x squared minus 4 as g, the function g, is R. But the domain of this one is, this should be positive. In other words, x lies between the closed interval from minus 3 to 3. So the intersection becomes this one from R, intersection of R with this one become this one. And same thing here. The product also, the intersection is from minus 3 to 3, which is the domain of f. Or when you divide them together, the same thing as well here. Here the domain, again, the same interval, except you have to exclude the roots of the denominator, of course. So you can't take x is equal to plus or minus 2. Here it's interesting because the square of f, you get 9 plus x squared. So it looks as if the domain is R. It's not true, because what you did, in fact, is you calculated the square root of 9 minus x squared, and then you squared the square root. So the square root, if you did two operations. So the first operation would not work unless x is in this interval, even if you square after that this square root. So the first square root would not work except in this interval, and therefore the domain of this particular function is also the domain of f, contrary to what it appears to be valid for all x elements in R. Now, we have to watch out for something. You can't just in calculus just add up any two functions like this one, for example. I can say, for example, suppose somebody asks you differentiate square root of minus x plus square root of x minus 2. What you do, you can say, for example, the derivative of this 1 over square root of 2 minus x, and this is, for example, 1 over square root of x minus 2, and you do this. But you can't do this, in fact. Why? Because here you have to make sure first that when you substitute x and it works here, it should work also here. For example, suppose x is equal to 2, then g exists, but x is equal to 2 here, f does not exist because it gives you minus 1. Again, if you take, for example, x is equal to minus 2, here it works, but here you have square root of minus 4. So you have to have, since the domain is the intersection of both functions f and j, then you have to make sure that both domains intersect. When then the domain of this function here, this has to be what inside the square root must be positive. So x is less than equal to 1. So the domain of f is the closed interval from minus infinity to 1, whereas the domain of j is the closed interval from 2 to infinity. Do these domains intersect? Of course, the intersection is void. And therefore, we say that this function does not exist because there is no one single x which can work out for both combination of functions, whether you add them up or you subtract them or you divide them, etc. And with this, we come up to the end of our lesson. And so in this lesson, we try to explain the meaning of a function, what's the meaning of a real function, and we listed the elements of a function to be the domain, the rule of the function, and the codomain. And we said that to summarize, a function is a mapping from two sets, from elements of two sets, from an independent variable into a dependent variable lying in an image set, and this image set is contained in set R because we are dealing with real numbers. And with this, we have come up to our lesson, and I We move on next time to a different lesson, and until we meet, I thank you for your attention and good luck.